Hello everyone, welcome to another video in which we'll be discussing previous year questions of JEST of statistical mechanics, right? So let's try the questions. Statistical mechanics, JEST questions. Okay, write down. Right, first question. Consider a system of particles. Consider a system of particles in three dimensions. In three dimensions with momentum p, with momentum p and energy energy E is equal to C P magnitude to C. C P magnitude, where C being a constant. Okay, C being a constant. The system is maintained at the system is maintained at system is maintained at inverse temperature beta, inverse temperature beta, volume V, volume V, and chemical potential mu, and chemical potential chemical potential mu. What is the grand partition function of the system? What is the grand partition function of the system? What is the grand partition function of the system? Is that alright? Consider a system of particles in three dimensions with momentum p and energy E is equal to Cp. System is maintained at inverse temperature beta, volume V, chemical potential mu. What is the grand partition function of the system? Okay, you are asked the grand partition function. This came in JEST 2012. Okay, can write down. Hang on. First of all, what is canonical partition function? Canonical canonical partition function. Zn is equal to 1 by hq integration of e to the power minus beta h dpx dpy dpz dx dy dz. Okay, integration of e to the minus beta h dpx dpy dpz dx dy dz, and we know e is equal to pc. Okay, e is equal to pc. So here, how to do this from here? See, if you see integration of dx dy dz is how much actually? It's actually dv, isn't it? Integration of dv, that means it's v. So I can take it out. So it will become v by hq integration of e to the power minus beta h dp. Okay, beta h dpx dpy dpz, and for dpx dpy dpz I can write what? For that, for the volume element of this one, I can write e to the power minus beta h. H is how much? Hamiltonian. H is energy actually. So beta E, this will become your how much? 4 pi p square dp. Remember this? So become 4 pi p square dp. Alright. Okay. Now let's take 4 pi also. 4 pi v by h cube. E to the power, what is E now? E is, we know, is given pc minus beta pc into p square dp. Okay, p square dp. Now, if you see, we know a formula 0 to infinity. This is all 0 to infinity. Okay, 0 to infinity, 0 to infinity. The upper limit is infinity. 0 to infinity e to the power x to the power m e to the power alpha x to the power n dx is equal to 1 by n gamma m plus 1 by n to alpha to the power n plus 1 by n. Okay, so here your aim is how much? 2. N is how much? Actually p to the power 1, so 1. So if you put 4 pi v by h cube 1 by 1 into gamma m plus 1, 2 plus 1 by 1 whole divided by alpha 2 plus 1 by 1. Okay, 4 pi v by h cube gamma 3 is actually 2, isn't it? 2 by alpha to the power q. Alright, yeah. Alpha, okay, alpha is how much here? Alpha is the coefficient of p, that is beta c. So just put beta c in place of alpha. 4 pi v by h cube 2 by beta c to the power q. Is that alright? Yeah. Yeah, so I can take this h inside, so it will be 8 pi v divided by beta hc whole cube. 8 pi v by beta hc whole cube. So this is your actually canonical partition function. Canonical partition function. Okay, this is z. Now, what is a grand canonical partition function? Grand canonical grand canonical partition function. Grand canonical partition function is how much? Well, zg, suppose grand canonical function is exponential. Inside the exponential e to the power mu by kt zn. Okay. Yes. Where your zn is the normal partition function. For example, this is zn. Alright. So let's write it as exponential mu by kt e to the power mu by kt, and zn is your 8 pi v by h beta hc whole cube. 8 pi v by beta hc whole cube. Yeah. So this is it. This will be your okay, and the 1 by kt I can write it as beta. So e to the power beta mu 8 pi v divided by beta hc. That will be your grand canonical partition function. Is it all right? Yeah. Just you have to remember this. Zg is equal to exponential e to the power mu by kt zn. Hmm? Okay, next question. Question number 2. Um, Consider a system maintained. Consider a system maintained at temperature T with two available energy states E1 and E2, each with degeneracies G1 and G2. Okay, if P1 and P2 are the probabilities are the probabilities of occupancy of the two energy states. Two energy states. What is the entropy of the system? What is the entropy of the system? Okay. Option A, S is equal to minus KB P1 ln P1 by G1 plus P2 ln P2 by G2. Option B, S is equal to minus KB P1 ln P1 G1 plus P2 ln P2 G2. Option C, minus KB P1 ln P1 to the power G1 plus P2 ln P2 to the power G2. Option D, S is equal to minus KB 1 by P1 ln P1 by G1 plus 1 by P2 ln P2 by G2. Okay, minus KB 1 by P1 ln P1 by G1 plus 1 by P2 ln P2 by G2. So the system maintain a temperature T1 with two available energy states E1 and E2 each with degeneracies G1 and G2. If P1 and P2 are the probabilities of occupancy of the two energy states, what's the entropy of the system? Okay. G1, so E1, E2 are there. Answer E1, E2, their degeneracies are G1, G2. Okay. So, what is the probability we know? Probability we know Pi is equal to summation Gi e to the power minus beta Ei by Z. Yeah, this is the probability, isn't it? This is the probability. So, if you see ln Py will be how much? From here, ln Gi plus ln e to the minus beta Ei minus ln Z. Yeah. So, if you see ln Pi is equal to ln Gi minus beta Ei minus ln Z. Okay. So, ln Pi minus ln Gi is equal to minus beta Ei minus ln Z. So, ln Pi by Gi is equal to minus beta Ei. See, your F free energy, Nmos free energy is minus kT ln Z. Okay. So ln Z will be how much? Or minus ln Z is here. Minus ln Z will be F by kT. Right. So in place of minus ln Z, I will put plus F by kT. Plus F by kT. Okay. So if you see, what is the question here? What is the entropy of the system? Okay. Entropy of the system is asked. Okay. Entropy of the system is how much actually? Minus scale K average value of ln Pi by J. This is the entropy of a system. So we need to find the average value of this. So how do this? If I do from here, ln Ei by Gi is equal to how much it will be minus beta average of Ei plus bit. Sorry, 1 by kt is actually beta plus f. Okay, so ln Ei by Gi expectation value, that is beta f. I can write like this: beta f minus beta e. Ei actually is Ei average value in Ei. So I can write it as ln Pi by Gi is equal to beta f minus u. Okay, average value VI I am writing as u. Alright. Hmm. Yeah. Now what? Now we know f is equal to u plus ts. So in place of f, I will put u plus ts. So ln pi by gi, sorry, pi by g is equal to beta u plus ts minus u ln pi by gi is equal to beta ts. Yeah. Okay. Now what is the form question we are asked? Entropy. We are asked entropy. Entropy S is equal to minus k ln pi by g average value. Okay, that is minus k. I can also write this as summation pi ln pi gi. Okay, so I can also, okay, see actually this one actually derived from this one. Okay, if you derived it, see, you got it this much, right? And from here you can keep s in this side and everything to this side, 1 by beta t. Okay, 1 by beta t ln pi by ga, and that is actually k, isn't it? Beta is 1 by k, but it's okay. Yeah, so k ln gi by, if the pi by gi is actually s. Okay, yeah, that's what I wrote here. Hmm. This one, so minus k, this one is what, p1 l ln p1 by g1 plus p2 ln p2 by g2. Is it all right? Hmm. Minus k p1 ln p1 g1 plus p2 ln p2 by g2. Okay. Next question. Question number 3. Collection of in two-level systems, two-level systems with energy is zero, with energy is zero and greater than zero, is in thermal equilibrium, is in thermal equilibrium at temperature T, at temperature T. For T tends to infinity, the specific heat approaches to collection of n two-level systems with energy 0 and E greater than 0 is in thermal equilibrium. Okay, so same JEST 2012 question is still going on. So the question is, the specific heat approaches to dash at T tends to infinity. So, so one energy is 0, another is E. Thermal equilibrium temperature T, for T tends to infinity, specific heat approaches to. So see, partition function z is equal to summation e to the power minus beta ei. Hmm? So summation gi e to the power minus beta e. So e to the power minus beta into 0 plus e to the power minus beta into e here, because there is degeneracy is 1. So this becomes 1 plus e to the power minus beta e. Okay, 1 plus e to the power minus beta e. So z is equal to 1 plus e to the power minus beta e. We are asked what? We are asked specific it. Okay, specific it. Okay, what is the formula for? First of all, formula for mean energy is how much? Minus del by del beta of ln z. Okay, so minus del by del beta of ln 1 plus e to the minus beta e. That will give me minus is there 1 plus e to the minus beta e, and now the derivative of this one is minus beta e to the power minus beta e. Sorry, minus e to the power minus beta e. So minus minus plus, so e to the power minus beta e divided by 1 plus e to the power minus beta e. This is our u. Now what is specific heat? Specific heat is how much? Specific heat. Specific heat is C is equal to du by dt. Du by dt. So d by dt of e to the power minus beta e divided by 1 plus e to the minus beta e. What is beta? Beta you can put, in place of beta we can put 1 by kVt. Yeah. So d by dt of e to the power minus e by kVt 1 plus minus e by kBt. Now we have to take the derivative here. Okay, take the derivative. E goes out, so 1 plus e to the minus e by kBt into derivative this one, that is minus 1 by minus e by kb t square, into e to the power minus e by kBt minus e to the minus e by kBt into this derivative this one minus e by kBt square, that is minus and plus, into e to the minus e by kBt whole divided by 1 plus e to the power minus e by kBt whole square. Yeah. So if you see, now instead of being e by kBt square, e by kBt square e to the minus k e by kBt plus e by kBt square, and those powers are cancelled. Alright, minus e to the power minus 2e by kBt square, so kBt into e to the e by kBt square, yeah, whole divided by 1 plus e to the power minus e by kBt whole square. Okay, so this is the one. But the thing is, t tends to infinity here. So everywhere you can just put infinity. So here if you put infinity, this will become, whole term becomes 0. This one becomes 0. This one becomes 0. So the whole terms becomes 0. So after a lot of this, after a lot of calculation, we got the answer as C. Right? So this is the answer. This is the answer. Is it alright? Here's the question number 3. Okay? Question number 3. Question number 4. Question number 4. Okay, right on. Consider three situations of four particles in one dimensional box of width L with hard walls. In case 1, the particles are particles are fermions. Case 2, they are bosons. Case 3, they are classical. Okay. If the total ground state energy, if the total ground state energy of the four particles in these three cases in these three cases are are EF, EB, ECl respectively, which of the following is true? Which of the following is true? Consider three situations of four particles in one-dimensional box of weight L with hard walls. In case the particles are fermions, they are bosons, they are classical. If the total ground state energy of the uh, four particles in these three cases are EF, EB, EL respectively, so the following is true. Options are EF is equal to EB, ECl, EF greater than EB is equal to ECl, EF is less than EB, less than ECl, EF is greater than EB, then ECl. Consider three situations of four particles in one-dimensional box of width L with hard walls. In case the particles are fermions, they are bosons, they are classical. Okay, four particles in one-dimensional box width L. Right. So, see, first let's consider the fermions. Let's consider the fermions. So, for fermions, we know like in one, like four particles are there now. In one state, there cannot be two fermions together like this, right? So only one fermion will be there, isn't it? Only only one fermion will be there. So only one fermion here, one here, one here, one here. So four. So this is a one-dimensional box. So this will be 1 into pi square h cut square by 2 ml square. 1 into 4 because this is n2 2 ml square. 1 into 9 pi square h cut square by 2 ml square. 1 into 16 pi square h cut square by 2 ml square. Okay. So the total energy will be how much? Pi square h cut square by 2 ml square. If I take common, it will be 1 plus 4 plus 9 plus 16. So 25 plus 5, that is 30. 30 pi square h cut square by 2 ml square, which is the ground state energy for EF. That means for fermions. For bosons, this is a case number 1. For bosons, all the particles can be in one state, correct? for bosons, all the particles can be in one state, isn't it? So one, two, three, four. There is no restriction here. So all are in particle first ground states of pi square h cut square by 2 ml square. So this is actually what? Yeah, this is 4 E naught. Suppose E1. E1 is a ground state. So this is actually 30 E1. This is 4 E1. This is 30 E1. Now your classical particles. Yeah, classical particles are also like they are also distinct. There is no restriction here. It's not like any Pauli exclusion crystal. Nothing else is there. So I can just arrange A, B, C, D distinguishable, but all can be in one state. So 4 into pi square h cut square by 2 ml square, which is actually 4E1, isn't it? So 4E1 I can write. So if you see, 4E1 is actually what? ECl. That means E classical. This is what? E boson. Huh? Boson. So actually E fermion is very greater than E boson, which is equal to E classical, isn't it? This is the case. I hope you understood this one. So this will be your option. Which option is coming? Option B. Yeah, option B. Okay, very good. Okay, next question. Question number 4. This came in JEST 2013. Okay, so the JEST, yeah, JEST 2013. This question. Next question is question number 5. Question number 5 is consider a system of two n non-interacting non-interacting spin half particles, each fixed in position, each fixed in position and carrying a magnetic moment mu, and carrying a magnetic moment mu. The system is immersed in a the system is immersed in a magnetic field B, in a magnetic field B. The number of spin up particles, number of spin up particles for which for which the entropy of the system will be maximum. Entropy of the system will be maximum is consider system to an non-interactive spin-up particles is fixed in position carrying a magnetic moment mu. The system is immersed in a magnetic field B. The number of spin-up particles for which the entropy of the system is maximum is option A 0, option B n, option C 2n, option D n by 2. This is just 2014. Okay, this is just 2014. This is a system of two n non-interacting spin-up particles, each fixed in position, carrying a magnetic moment mu. The system is immersed in a magnetic field B. The number of spin-up particles for which the entropy of the system will be maximum is System of two and non-interacting spin-up particles, each fixed in position, carrying a magnetic moment mu. System is immersed in a magnetic field B. The number of spin-up particles for which the entropy of the system will be maximum. As okay, there are, for example, there like two and non-interacting spin-up part. Okay, sorry, we have done this kind of question in our previous sessions. Two and non-interacting spin-up particles. Okay, so that means spin up and spin down. So yeah, spin up and spin down will be there. So for example, spin up be n. Okay, n particles are spin up, and how many are spin down then? Spin down will be total is 2n. So spin down will be 2n minus n. Okay, 2n minus n particles. Okay, 2n minus n particles. So the number of ways for arranging this kind of particles. Okay, so number of ways will be what? 2nc n for spin up, number of arrangements, and 2nc 2n minus n is your spin down. Yeah, spin down. All right. Now what is the question? The entropy, number of spin up particles for which the entropy will be maximum. That means what we have to do exactly? That means spin entropy is your S, number of spin up particles for which entropy will be maximum. This ds by d small n, because small n is your but number of spin up particles. So we have to take the derivative with respect to small n and make it to 0. That will be our what? This one. Number of ways means number of microseconds, that is omega. Okay, omega is this much. All right, and omega is like it's same. It's the same thing. Okay, so we know entropy is what? K ln omega, isn't it? K ln omega. So let's write K ln total omega here. Big what? Summation K ln omega. Big what here? These two. So like it's like omega 1 into omega 2, isn't it? Right? It's like omega 1. Suppose this is omega 1. So omega 2. So omega is actually your omega 1 into omega 2. Microstate is actually multiplied. So omega 1 into omega 2, which is ln mn. Log mn is log n plus log n. So ln omega 1 plus k ln omega 2. Is it alright? So k ln omega 1 is how much? 2n cn plus k ln 2n c 2n minus n. Is it alright? Now you have to open it. K ln 2n factorial divided by 2n minus n factorial into n factorial plus k ln 2n factorial divided by 2n minus 2n plus n factorial into 2n minus n factorial, which is actually both of the same things, k 2ln, this is 2n factorial, or divided by 2n minus n factorial into n factorial plus k ln 2n factorial. This is actually what? N factorial into 2n minus n factorial. Okay, yeah. So that will give me, see, these are two same things. So I can write as 2k ln 2n factorial all divided by 2n minus n factorial into n factorial. Okay. Okay, so we will use Stalling approximation 2 ln 2k ln 2n factorial minus ln 2n minus n factorial minus ln n factorial, which is equal to 2k 2n ln 2n minus 2n minus 2n minus n ln 2n minus n minus 2n plus n minus n ln n plus n. Hmm. So if you see, If you see this, this is okay, right. Yeah. So we have to do what ds by dn is equal to 0. So if we do the derivative from here, you will see this term 0 0. This is what? This is actually what minus 2n minus n divided by this 2 minus n, and the derivative of this again, that is minus 1, that is plus 1. Okay. Plus 1 for this derivative. This is 0. Now minus n by n. Okay, and this is plus 1 is equal to 0. Okay, so this is your 1. Hmm. You're doing a mistake. Okay, I have missed a term here. This is plus for this derivative and ln to n minus n. Okay, okay, that is equal to 0. So this is 1. This is also 1 cancelled. So 2 plus ln to n minus n is equal to 0. Yeah. Uh, Again, I'm doing a mistake. There is some mistake here. Okay, let me write the derivative. Okay, I have missed this term again. The derivative. Let me write the derivative again. So ds by dn is equal to 0. So the derivative will be minus 1 plus 2n minus n by 2n minus n plus ln 2n minus n minus ln n is equal to 0. That is, this is 0. So ln 2n minus n by n is equal to 0. Ln m minus ln n is ln m by n. So that is 2n minus n by n is equal to 1. E to the power 0 is 1. So 2n is equal minus n is equal to n. So 2n is equal to 2n. So n is equal to n. That's what it is. Okay. So number of, so n is equal to actually n. So number of spin up particles for which ds is like entropy is maximum is how much? The answer is, because we found number of spin up particles is small n, and small h we found as capital N. Okay. So this is it clear? I hope it's clear. Okay, next question. Question number, this was question number 5. Next question number 6. It's from just 2016. Question number 6 is a two-dimensional box, a 2D box in a uniform magnetic field. In a uniform magnetic field, B contains n by 2 localized spin half particles, with magnetic moment mu, and n by 2 free spinless particles n by 2 free spinless particles which do not interact, which don't interact, which don't interact with each other, which don't interact with each other. The average energy of the system, the average energy of the system at temperature T is at temperature T is how much? This is just 2016. Option A 3 nkt minus half n mu sin n mu b sin hyperbolic mu b by kbt. Option B nkt minus half n mu b tan hyperbolic mu b by kbt. Option C half nkt minus half n mu b tan hyperbolic mu b by kbt. Option D 3 by 2 nkt plus half n mu b cos h mu b by kbt. Is that all right? Is it all right? Yeah. So solve this question. 2D box in a uniform magnetic field. In a uniform magnetic field, B contains n by 2 localized spinor particles with magnetic moment mu and n by 2 free spinless particles which do not interact with each other. Okay, is it all right? So write down. It's a good question. For n by 2 free particles, for n by 2 free particles in one dimension, okay, n by 2 free particles in one dimension, average energy is what? Average energy. Average energy is n by 2 kt. Average energy is n by 2 kt. And for n by 2 localized, n by 2 localized spinor particles, average energy is minus half n mu b tan hyperbolic ub by kbt. Okay, the average energy at temperature T is the average energy at temperature T is how much? It will be what? This is the average energy for n by 2 localized spinor particles. Okay, at temperature 2 would be nkt by 2 minus what? This is your nkt by 2 for free particles in one dimension. Now for localized spin half particles, this so we just will add them half n mu b tan hyperbolic mu b by kbt. Yeah, is that all right? Okay. Okay, next is a very good question. It's like same kind of thing, but it's a bit like different, like different way it's asked. So you won't face any problem, but just let's do it. Like this type of question also may come. This will be question number 7, I think. Question number 7. The energy spectrum of a particle consists of four states with energies 0, epsilon naught, 2 epsilon naught, and 3 epsilon naught. Let Z B T Z F T and same type of question we have done, but with different twist. Denotes denotes the canonical partition functions. The partition function. The canonical partition functions for four non-interacting particles at a temperature T temperature T. The subscripts B, F, and C represent bosons, fermions, and and classical classical particles, distinguishable classical particles, respectively. respectively. Let y is equal to exponential minus epsilon by kbt. Hmm. So, which one of the following statements, which one of the following statements is true about ZBT, ZFT, and ZCT, respectively? Okay. Options are: option A, they are polynomials in y of degree 12, 6, 12, respectively. Again, they are polynomial of y in degree 16, 10, 16, respectively. They are polynomials in y of degree 9, 6, 12, respectively. And they are polynomials of y degree 12, 10, 16, respectively. Is that alright? Okay. The energy spectrum of a particle consists of four states with energies 0, epsilon, 2 epsilon, and 3 epsilon. Let ZBT, ZFT, ZCT denotes the canonical partition functions for the four non-interacting particles at temperature T. Subscripts B, F, and C represent bosons, fermions, and distinguishable classical particles, respectively. Let y is equal to exponential minus epsilon by kBt. Which one of the following statements is true about ZBT, ZFT, and ZCT, respectively? Is that alright? Let's try. This question came in just 2019. So see, four particles and energy levels are also 4, 0, epsilon, 2 epsilon, 3 epsilon, epsilon, 2 epsilon, 3 epsilon. What is it asked in the question? Um, let this be, okay, let y is equal to this much. Denotes the canonical particle function of four interacting particles at temperature T. The energy spectrum of a given this is. Okay, so how to arrange the particles? So the following statements is true about this. Okay, okay, see. So here we will take the maximum energy because if you see the options, the degrees are like we need maximum kind of energy here. So for example, this is boson. For bosons, all the four particles can be here. There is no restriction for boson, right? So this is how much? Energy is how much? 12 epsilon. Hmm. Energy is a 12. Energy is a what? 12 epsilon. Right. So Z b to the power minus 12 epsilon by kBt. And we know y is how much? Epsilon minus exponential minus epsilon by kBt. So this I can write as a y to the power 12, right? Right. So for bosons, the this one is 12. Got it. So option for bosons, this is boson, fermion, classical. So the option like power of y is what in it is asked polynomial in y of degree. So b is 12, 12. So these two can be the options. These two options are discarded now. Next, let's go to fermion. If you go to fermions, again 4 states 0, epsilon, 2 epsilon, 3 epsilon. Now see fermions here. We can arrange them in 2, 2, right? We can arrange them in 2, 2, right? Okay. So see, I can have two fermions here and two fermions here. Okay, this will be 6 epsilon plus 4 epsilon. That is 10 epsilon. So y is equal to what? E to the power minus 10 epsilon by kBt. Sorry, z. Zf, which is y to the power 10, isn't it? So the answer is here. Okay, 10. Okay, now classical. Okay, again classical also we can arrange everything in the upper state. All four, no restriction. So actually this fermion, I'm sorry, fermions, how can they be in the state? Fermions cannot be in the same state, right? The fermions cannot be in the same state. So this is here one, two, three, four. All four here. So the total energy would be what? 3 plus 2 plus 1. That is 6 epsilon. So the answer will be y to the power 6. Okay, because y to the power minus 6 epsilon by kBt. Y to the power 6. The answer is 6 here. And for classical again, it is 4 particles here. So that would be 12. Y to the power 12. So answer is what? 12, 6, 12. Okay, polynomials of y. 12, 6, 12. Yeah, that will be the answer. Got it? Is it clear? Is it clear? Okay. I hope you understood. It's a very good question it was. And yeah, these are some of the questions from JEST we did in statistical mechanics. And please keep like tuned to the channel so that we can have more videos to it. I hope you're enjoying the videos. You're watching the videos and understanding the concepts. If you have any doubt, you can let me know in my Telegram channel, which I will give in the description below. And yeah, please keep watching and share if possible. Okay, yeah, thank you very much.